Hey everyone, welcome back. Today we're doing a deep dive on something that sounds, I don't know, maybe a little bit basic at first,
Yeah,
the Atwood machine.
right.
You wanted to get a really good grasp on this classic physics concept.
Hmm.
So we've gathered articles, simulations, even some hands-on guides
Yeah.
to kind of break it all down for you.
It really is fascinating how much you can learn from something that's basically just, two weights,
Yeah.
a string and a pulley.
Yeah, all the sources emphasize how basic the setup is, but
Right.
I'm guessing there's got to be more to it than meets the eye,
Oh, absolutely.
if it's this important in physics.
Yeah.
So what makes this so special?
Well, the Atwood machine, it's really like a perfect little world for exploring like all these core ideas in physics. You can
Okay.
see Newton's laws in action,
Yeah.
understand how gravity works. You can even start to wrap your head around things like energy conservation.
Energy conservation, I've always found that whole thing kind of mind-boggling.
It's a big one.
It is, and the source mentioned that it's connected to the Atwood machine somehow. Can you help me see how that works?
Absolutely. So picture those two weights, right? And they're moving.
Right.
As one weight goes down, it's losing potential energy, right, because of gravity.
Mm-hmm.
But that energy, it doesn't just disappear.
Right.
It gets transferred to the other weight as it goes up.
Okay.
And the Atwood machine lets you see that exchange,
Wow.
that elegant exchange of energy happening right there in front of you.
So it's like a little energy dance
Yeah, exactly.
between the weights?
Exactly.
Okay, I think I'm starting to get that a little bit.
Good.
But something else that the sources kept bringing up was how different a real Atwood machine is
Right.
from the kind of the ideal one you see in textbooks.
Yeah.
What's the deal with that?
Well, in an ideal world, we pretend that things like friction and air resistance don't exist.
Ah, okay.
But in the real world, they totally do. So, for example, even just a tiny little bit of friction in the pulley
Yeah.
can change how those weights move.
The source even mentioned that the string itself
Yeah.
having some mass can affect things.
It's true.
I never would thought of that.
And then also the string, stretching a little bit,
Oh, okay.
that elasticity, it can have a small impact too.
Interesting.
Imagine you've got two weights that are almost exactly the same
Okay.
on your Atwood machine.
Okay.
And in a perfect world, they would, move really slowly,
Right.
barely budge, but add in a touch of friction
Yeah.
in that pulley, and all of a sudden, the lighter one might not move at all.
So it's all about understanding those kind of subtle differences
Absolutely.
between the ideal and the real world.
Yeah.
Okay, so far we've been talking about the Atwood machine as this physics lab thing.
Mm-hmm.
But how does any of this relate to like me out in the real world?
Oh, you'd be surprised. How many everyday things
Mm.
actually use the same ideas behind the Atwood machine?
Really?
Oh, yeah.
So
Elevators, for example.
elevator.
They use a similar system of weights and cables to go up and down smoothly.
So you're telling me there's like a hidden Atwood machine inside every elevator I've ever ridden?
Exactly. Think about it.
Okay.
You've got the elevator car that's one weight,
Okay.
and then there's a big counterweight
Right.
attached to the other end of the cables.
Okay.
The cables act like our string,
Yeah.
and the motor system is like our pulley.
Gotcha.
And by adjusting that counterweight, engineers can control how much force is needed
Okay.
to move the elevator up and down safely.
That's actually really cool. I never would guess that.
Yeah.
And I bet knowing about the Atwood machine makes me appreciate those elevator rides even more now.
For sure.
So what else uses this kind of system?
Oh, lots of things. Cranes for lifting heavy objects.
Okay.
Some types of amusement park rides.
Yeah.
Even some cable car systems that, move people up mountains.
Okay.
It's all about balancing forces
Mm-hmm.
and controlling motion in a clever way.
Okay, so I'm really seeing how this seemingly simple concept
Yeah.
is actually like pretty powerful
Yeah.
and all around us. It's like
Yeah.
a secret code to understanding how things work.
I like that.
Speaking of understanding, our sources also talk a lot about how the Atwood machine is great for hands-on learning.
Oh, yeah, for sure.
Like what's
Cool.
the big deal with that?
Well, one of the websites we looked at, it even had instructions for building your own Atwood machine.
Right.
And they weren't kidding about the safety precautions.
Yeah, no runaway weights allowed.
Exactly.
But seriously, why is building one yourself so helpful?
Well, because actually doing something helps you understand it
Okay.
so much better than just reading about it,
Yeah.
The source even mentioned how Like students
Yeah.
often have misconceptions about forces in motion. And actually seeing those forces in action with an Atwood machine can really clear things up.
Okay, that makes sense.
Yeah.
Oh, and before I forget, the sources mentioned something called a modified Atwood machine.
Oh, yeah.
What makes it different?
So in a modified Atwood machine, you basically change things up a little bit.
Okay.
So one of the weights can move horizontally
Okay.
instead of just straight up and down.
So it's like adding another dimension to the whole experiment?
Exactly.
Okay, so why would you want to do that?
Well, it lets you explore more complex situations
Okay.
and see how things like inclines and friction change the way things move.
Mm-hmm.
You know, it's getting closer to how things actually work in the real world,
Right.
where you rarely have this like perfectly straight up and down movement.
Yeah, good point.
Yeah.
All right, so even with a simple tweak like that,
Right.
the Atwood machine can get a lot more sophisticated.
It can.
This is way more interesting than I thought it would be.
I know, right?
Yeah.
It's pretty cool stuff.
Okay, so we've laid the groundwork. We kind of understand what the Atwood machine is all about.
Mm-hmm.
Where do we go from here?
Well, in the next part of our deep dive, we're gonna explore some practical experiments
Okay.
that you can actually do with an Atwood machine.
Okay.
And we'll even look at how it can be used to calculate the acceleration due to gravity.
Oh, wow.
It's going to be a fascinating journey.
All right, I'm ready for it. Stay tuned, everyone, because we're about to take our Atwood machine knowledge to a whole other level.
Definitely.
All right, see you in part 2.
See ya.
Welcome back. So we've kind of established that the Atwood machine,
Yeah.
pretty basic looking, but actually a big deal in physics.
Right.
And get this, the source material we have, it actually walks us through like how to do experiments with one.
Mm-hmm.
I gotta admit, I'm kind of intrigued.
Yeah, it is pretty cool
Yeah.
how you can explore all these like fundamental physics concepts
Right.
with such a simple setup.
Yeah, they stressed being super careful with measurements.
Oh yeah.
Like they even suggested using a stopwatch to time how long it takes those weights to move a certain distance.
Yeah.
I guess every millisecond counts, huh?
Absolutely. Precise measurements are key
Okay.
to getting accurate results.
Gotcha.
And that's why the sources recommend using these special weights called slotted masses.
Slotted mass.
Yeah, they let you adjust the weights
Okay.
on each side really precisely.
Okay, so slotted masses. Got it.
Yeah.
What else did they say about getting good results?
Well, they emphasize the importance of keeping certain things constant.
Okay.
Like the total mass of the system should stay the same.
Mm-hmm.
So you're only changing the difference in mass
Okay.
between the two weights.
Okay.
It's all about isolating the variables, to see what really makes a difference.
Right, so it's like you're controlling the experiment to make sure you're only testing one thing at a time.
Yep.
Classic scientific method stuff.
Exactly.
Oh, and speaking of scientific methods,
Yeah.
they mentioned something called a free body diagram.
Oh, yeah.
What in the world is that?
Free body diagrams, they're super helpful for visualizing the forces that are at play.
Okay.
So imagine you're looking at just one of the weights
Okay.
that's hanging from the string.
Okay.
You've got gravity pulling it down,
Yeah.
right?
Right.
And then you've got the tension in the string pulling it up.
Mm-hmm.
A free body diagram basically helps you see those forces
Okay.
and understand how they're interacting.
So it's like a little diagram showing all the pushes and pulls
Exactly.
on that weight.
Yeah.
Okay. That actually makes a lot of sense.
Yeah.
And if I'm remembering right, the source said that the difference between those two forces, the gravity pull and the string tension, that's what determines how fast the whole system accelerates.
You got it. And by analyzing those forces,
Yeah.
on your free body diagram, you can use something called Newton's second law
Okay.
to actually predict how the weights will move.
Okay, confession time. I'm a little fuzzy on Newton's second law.
Okay.
Isn't that the one that's like for every action there's an equal and opposite reaction?
That's actually Newton's third law.
Oh, okay.
His second law is all about how forces and acceleration are related.
Okay.
Basically, he says that the force acting on an object is equal to its mass times its acceleration.
Okay.
So if you know the forces involved, you can figure out how quickly
Gotcha.
the object will speed up or slow down.
Okay, so that's how it all that's how it all ties together.
Yeah.
But even with all this careful planning, like the source pointed out, there's still things that can mess up your experiment.
Oh, definitely. Like what?
Well, they mentioned things like friction in the pulley,
Right.
which we talked about earlier.
Yeah. Even a little bit of friction can throw off your results.
Okay.
They also said it's important to make sure that the string is running smoothly.
Okay.
And not, rubbing against anything.
Right.
Because that can also create extra friction.
Wow. So it seems like setting up a truly accurate Atwood machine experiment is a lot trickier than it looks.
It can be. It can be.
You really have to pay attention to all those little details.
You do.
But I guess that's what makes it good science, right?
Exactly. It's all about identifying those potential sources of error.
Okay.
And trying to minimize their impact.
Gotcha.
That's how you get, reliable and meaningful data.
Okay, so far so good.
Yeah.
But there's one thing in the source material that really blew my mind.
Okay.
You can actually use the Atwood machine to calculate the acceleration due to gravity.
It's true.
That G value we always hear about.
That's right. That's right.
That's crazy.
Yeah, by carefully measuring the masses and the acceleration of the system.
Okay.
You can rearrange the equations we've been talking about, and you can solve for G. It's a pretty amazing way to demonstrate a fundamental constant in physics.
Yeah.
Using a relatively simple experiment.
That's incredible. But how accurate can those calculations really be?
Right.
I mean, we just talked about all those sources of error.
Right. It all depends on how precisely you measure things.
Okay.
And how well you control for those errors.
Yeah.
But even with a basic setup, you can get a pretty good estimate of G.
So it's not just a theoretical exercise.
No.
You can actually get real-world results.
Real-world results for sure.
I'm really starting to see the power of this Atwood machine, and it gets even more interesting when we bring in that modified version we talked about earlier.
Exactly. Yeah.
The source suggested using the modified Atwood machine,
Yeah.
where one weight moves horizontally to explore even more complex scenarios. Like what happens when you change the angle of the incline that weight is sliding on.
Exactly. And they even challenged us to figure out how to measure the friction between the weight and the table.
Yeah.
Without using any fancy equipment.
I know, right.
It's a great example of how a simple experiment can spark some really creative problem solving.
Totally.
And they hinted that we might need to think about energy.
All right.
To solve that one.
Okay, color me officially impressed. This deep dive has been way more enlightening than I ever expected.
It's pretty cool stuff.
Yeah, I thought we were just talking about two weights and a string.
Right.
But it turns out the Atwood machine unlocks a whole world of physics.
A whole world, yeah.
And we're not done yet.
Not even close.
So what's next?
Well, in the final part of our exploration,
okay,
we're gonna connect these experimental insights, back to those real world applications.
Okay.
And we'll leave you with some thought-provoking questions to ponder.
Can't wait. Stay tuned, listeners.
Yeah.
Because the grand finale of our Atwood machine adventure is coming up next.
All right, we're back for the final part of our Atwood machine deep dive.
I have to say, I started this thinking it'd be, pretty basic.
Yeah.
But I've learned so much.
Good.
I'm starting to see this simple setup in a whole new light.
Yeah, it's amazing how much you can unpack.
Right.
From something so seemingly straightforward. Right.
Yeah.
We've gone from the core concept to hands-on experiments. We even touched on how to calculate gravity with this thing.
I know, it's crazy. And all those potential sources of error.
Yeah.
Who knew there were so many things that could mess up your results. It really makes you appreciate the precision
it does
needed for good science.
Yeah.
But what I'm really curious about now is how all this connects back to the real world.
Yeah.
We talked about elevators before.
Right.
But what other examples are there?
Well, think about cable cars. That carry skiers up mountains.
Yeah.
They use a counterweight system that's very similar to an Atwood machine. It helps to balance the weight of the car, makes the whole system more efficient.
So next time I'm on a ski trip, I can impress everyone.
There you go.
With my Atwood machine knowledge.
That's right.
While effortlessly gliding up the slopes.
Exactly.
But seriously, are there any other examples that aren't about going up mountains?
Of course, yeah. Funicular railways.
Funicular railways?
Yeah, you know those trains that go up steep inclines?
Yeah.
They often use a modified Atwood machine setup.
Hmm.
You've got the train car on one track, a heavy counterweight on a parallel track.
Okay.
And the cables and pulley system helps to control the movement up and down the hill.
Wow. So it's not just about like ski lifts and mountain trains.
Yeah.
These are systems that people rely on every day.
Every day, yeah.
It's pretty mind-blowing how a concept that's been around for centuries
I know, right?
is still so relevant to modern engineering.
It really is.
It speaks to the power of fundamental principles, I guess.
It does, yeah.
Once you understand those building blocks,
Mm-hmm.
you can see them working everywhere.
Everywhere.
And speaking of building blocks, the source even hinted at the Atwood machine's relevance to something totally unexpected. Space exploration.
Sure.
Space exploration. And that's seriously far out. What could the Atwood machine possibly have to do with space?
Well, I imagine, two spacecraft connected by a tether, kind of like our string. That tension in the tether could be used to control their relative motion.
Huh.
Just like in our Atwood machine.
Wow.
It could be crucial for things like docking maneuvers.
Okay.
Or even transferring cargo between spacecraft.
So the Atwood machine, from physics classrooms to the final frontier.
That's right.
I'm starting to think there's no limit to what this simple setup can teach us.
It's amazing, isn't it?
What would you say is the most important takeaway from all this?
That's a good question. I think it's the importance of curiosity.
Okay.
And digging deeper. The Atwood machine might look simple.
Yeah.
But it embodies all these powerful principles that shape our world.
Yeah.
And by understanding those fundamentals, we can better appreciate the technology around us.
Mm-hmm.
And maybe even spark ideas for future innovations.
That's a great point.
Yeah.
And speaking of sparking ideas, the source got me thinking.
Okay.
Could you design an experiment using an Atwood machine to measure the energy lost due to friction?
Oh, interesting.
I mean, we know friction is a big factor in real-world systems.
It is, yeah. That's a fantastic question. It really shows how the Atwood machine can inspire further exploration, and yeah, I think it's possible.
Okay.
Maybe by carefully measuring the starting and ending speeds of those weights. We could calculate how much energy was lost.
Right.
And that lost energy would be due to friction.
That's definitely something to ponder.
It is.
Who knows? Maybe one of our listeners will be inspired to tackle that challenge.
You never know.
The resources that we've explored in this deep dive.
Right.
They're a great starting point, but there's a whole universe of information out there.
Oh yeah.
Waiting to be discovered.
Absolutely.
Well said. So to wrap up this epic Atwood machine adventure, I wanna encourage everyone listening.
Yeah.
Stay curious, keep exploring, and never stop asking questions about the world around you.
For sure.
You never know what fascinating discoveries you might make.
Couldn't agree more.
All right, that's a wrap on our Atwood machine deep dive.
It is.
We hope you enjoyed the journey.
We did.
Until next time. Keep those brains buzzing.
Keep them buzzing.